Hello, this is Mahendra Didia. This is the second related video in Module 2 in On-Demand Dynamic Supplemental Book on Liquid Formulation. The scientific discipline of physicochemical characterizations, in this case solution dosage form, is an integral part of development of innovative product, and it is the focus of this book. The second module focuses on physicochemical characterization, and in this submodule we'll look at pH pKa relationships, cosolvent and complexation, how they affect solubility of the solute. The pH of solution and solutes pKa are critical in determining solute solubility. Many solutes are either weak acid or weak bases. If the solute is neutral, then it's unaffected by pH. The solubility of weak acid and weak bases, and it depends on the pH of the solution according to Henderson-Hasselbalch equation as shown below. Acetic acid loses its hydrogen in presence of water and forms acetate moiety. Water, on the other hand, gains hydrogen and forms H3O with a positive charge. This is non-ionic species of acetic acid. Acetate is ionic species. And the pH of the solution, the log concentration of H3O or H plus. So for weak acid, pH is equal to pKa, dissociation constant, plus log of ionized concentration of A minus divided by unionized concentration of the molecule, in this case HA. For weak base, its pH is equal to pKa plus log of unionized base divided by ionized base pH plus. And it's shown in this graph. This graph is extremely important to understand how solutions will form ionic and unionic or non-ionic. And ionized form are more soluble compared to unionized species. And we will see that unionized species is extremely important for activity of the compounds. For acidic, when pH is greater than pKa, they are more ionized and therefore more soluble, as difference between pH and pKa is greater. And they are less soluble in acidic solution. Basics shown in a blue are more ionized in acidic condition. pH minus pKa is negative, whereas they are less soluble in basic condition. pH is greater than pKa. So acids are more soluble in basic pH environment, and bases are more soluble in acidic environment. This particular graph shows for acidic molecule, if the difference between pH and pKa is minus 0.3, almost 60% will be in non-ionized. If pH minus pKa is greater than 1, as shown here, less than 10% will be in non-ionized form. Rest of that will be in ionized form. Acid will dissolve more in this pH. So let's look at the practical example. Preservative pKa and solution of pH. When would the preservative be effective? Unionized preservative species disrupt microbes, cell wall synthesis, and protein synthesis. So we want to have unionized species at the microbe's cell site. Products containing water, sugar, and other aqueous liquids needs to be preserved. to prevent contamination of microbial growth throughout shelf life. So pH pKa relationship becomes very important. On one hand, we want to make sure preservative is soluble in solution dosage form, and on other hand, we want preservative to be unionized to be very active. So these two needs to be balanced. We can calculate unionized species to ionized species is 10 raised to the difference between pK and pH. And the required concentration of preservative to be effective is essentially effective form concentration. Convert that into a percent divided by percent anion. We will see that in sorbic acid, which has pKa of 4.76. We know from literature that effective form requires concentration of 0.13% for preservative effective. Solution must have at least 0.13% of unionized species of sorbic acid to be effective. We can look at the pH of solution between 4.5 to 5.5 to 6. These are very commonly used in pharmaceutical oral solutions as well as in cosmetic. The percent of effective form can be calculated from this equation, unionized versus ionized is equal to 10 raised to pK minus pH. And at different pHs, from 64% to 18% to 3.98%. And we can calculate the concentration of sorbic acid required in the solution to maintain its preservative effectiveness through shelf life. An example shown here at the bottom is for pH 6. Unionized versus ionized species is given by 10 raised to 4.6 minus 6. This is 0.0398 or 3.98%. Required concentration is 0.13 multiplied by 100 divided by 3.98%. So we need 3.27% of sorbic acid present in the solution throughout its shelf life. That's a very high concentration of sorbic acid in the solution. But that's what will be required at pH 6. Whereas at pH 4.5, 0.2% will be required. At pH 2.76, essentially all of the sorbic acid will exist as unionized or effective. However, pH 2.76 is going to be very low and acidic. So this needs to be considered in formulation dosage form. Another aspect is antioxidant effective pH range. Oxidants are reactive oxygen species. So oxidants have an oxygen species ROS. It's a free radical or free radical precursor. Shown here as O2 free radical, oxygen free radical is an oxidant, HO2. It's a very active oxidizing agent. O2 free radical will react with HO2 and will form hydrogen peroxide and free oxygen. And products will oxidize in the presence of H2O2 and oxygen. Similarly, two O2 free radicals and hydrogen ions generated at different pHs will form H2O2 and oxygen. Again, these are very reactive. So antioxidants are used to sequester free radicals. Ascorbic acid, which has pK of 4.17, is well known as antioxidant in pH range of 5.5 to 7. More ionized, pH is greater than pKa. So key to using ascorbic acid as an antioxidant is pH-pK relationship. Ascorbic acid by itself is not antioxidant. It is the ascorbate, the ionic species. The ionic pieces will capture the free radical and will form ascorbate free radical that will neutralize, rearrange itself to dihydroxy ascorbate. We need to adjust pH of ascorbic acid formulation to 5.5 to 7, which is a reasonable range for most oral and cosmetic products. The picture below shows fresh foundation in cosmetic and then oxidized, changing its color. So to stop foundation from oxidizing, we need to add antioxidant. Cosolvents. Cosolvents are commonly used in pharmaceutical as well as cosmetic products. Solutes, again, weakly electrolyte and nonpolar molecules will have a poor water solubility. Co-solvent have two properties. One, they are miscible in water through hydrogen bond of hydrophilic group. Ethanol having a hydrophilic OH group that makes it water miscible. Second property co-solvent has is or solute are soluble either through weak electrolyte or through hydrophobic regions such as London dispersion. We saw that in the first related video of module 2, how retinol and ethanol soluble are through hydrophobic region. So molecular interactions of co-solvent is hydrophobic regions interferes with the water hydrogen bonding net. It disrupts water's intramolecular forces, and therefore co-solvent reduces water's ability to separate nonpolar solutes. Thus, it increases its solubility. London dispersion forces between hydrophobic portions of co-solvent and solute. They play extremely important role. An example shown here is a ketoprofen drug is ROH in the following diagram, and polyethylene glycol has an OH group and a non-polar moiety, and PEG 400 is generally used as a co-solvent with water. So when we mix just the water and ketoprofen drug and stir it and mix it, it will separate. Reason for separation is water molecule will form hydrogen bond and squeeze the drug out. Co-solvent when it's added, such as PEG 400, drug and PEG, London dispersion force. This will disrupt hydrogen bonding between water molecules and will dissolve ketoprofen into a mixture of PEG 400, polyethylene glycol, and water as a co-solvent. So key to using a co-solvent is to disrupt water's intramolecular forces and have sufficient London dispersion forces between co-solvent and a solvent. Complexation. Beta-cyclodextrins are well known and they're used to increase the solubility by complexation. We published effect of cyclodextrin ring size, effect of pH and temperature in complexation. Complexing agent has a hydrophobic core and hydrophilic shell. So this has OH in the outer portion of it. That's hydrophilic shell and hydrophobic core. Molecular interaction is solute, which is insoluble or poorly soluble in water, is partly or completely enveloped by complexing agent. Either solute sits in the center of it and thereby increases its solubility. In this video, you will see molecular simulations of how solute sits in this particular cavity. This is BCD, beta-cyclodextrin, having a shell an inner core, insoluble material or material that's soluble within the inner core. It will fit in that ring cavity and make a soluble product. Here is insoluble material sitting into the cavity itself. So outside is exposed with our OH group, allows us to dissolve in water, and inside is a non-polar cavity which solubilizes non-polar molecules.